All right, hi everyone. This is the last example from chapter 7. It is question 155. So in question 155, we are going to be charging a capacitor. So we got a voltage, a capacitor, and a resistance. Let's read the question. So question 155, a capacitor of 1 microfarad and a resistor of 10 mega ohm are connected in series. If we apply a voltage of 20 volt, what will be the voltage drop across the capacitor and resistor after A, immediately after we apply the voltage, B, 5 seconds after we apply the voltage, C, a very long time after we apply the voltage, in other words, in a time of infinity. So let's start with part A. So there's a couple of points we need to mention first. The resistance across the voltage drop across the resistor is equal to the current multiplied by the resistance, and it's equal to the voltage across the resistor. From the point of view of the capacitor, the voltage, and we have the capacitor formula over here, the voltage is equal to the charge divided by the capacitor, all right? So in other words, if we can find the charge at a given time, we can find the voltage drop across the capacitor. All right, makes sense. Now, a capacitor in this format is still subject to Kirchhoff's law. So we can use the loop rule over here. So let's say we start over here. We go in that direction, and it's reasonable to think, since we are charging, that the current is going to go upward following the current from the battery. So it's going in that direction. We have a voltage gain, 20 volt. We have drop in voltage on the capacitor, minus QC, so using this one. We have a voltage drop across the resistor, minus IR. All right, this has to equal 0 also. So 20 has to equal these two terms together. Okay, so basically the goal is to find the charge at some given time. At time 0, t is equal to 0 here. Exponential of 0 is equal to 1. 1 minus 1 is equal to 0. So this term becomes 0. The charge is 0. This term becomes 0. 20 minus 0, what is the voltage drop on the resistor? Well, this one is simple. So the voltage drop, and I'm going to write VC over here for the voltage drop of the capacitor. It is 0. There's no charge on the capacitor. VR, well, just like in this case, when we open right away the circuit, it's like if there's a wire. It's like there's no capacitor at the beginning. So all the voltage drop is across the resistor. So voltage of the resistor is 20 volt. All right. I'm gonna solve part C before part B, by the way, because part B will require multiple steps. All right. Part C is the other extreme. We are being asked at a very long time. Now, very long time mean infinity, basically. So when we look at this formula, at a very long time, this becomes minus infinity. Exponent minus infinity, this term becomes 0. That means the charge is equal to CV. Okay, so here's the irony. The charge is equal to CV over here. So we replace over here minus, the Q becomes CV. So just make sure here. So that's implied that 20 minus CV divided by C minus IR is equal to 0. Now V is 20 and the C cancel out. So we got 20 minus IR is equal to 0. Well, that's kind of obvious that VC, this is the voltage across the capacitor, VC is equal to 20 volt. VR is equal to 0. After a very long time, there's no current, mean there's no voltage drop on the resistor. All the voltage drop is across the capacitor in this case. All right, now let's go to part B because it's slightly different. We need to calculate the charge at a given time if we want to figure out what is the voltage across everything. So we won't need this. Will we? Okay, actually, I'm going to erase nearly everything. We need some more room for this calculation. I will need the loop rule though. So I'm going to write it again over here. Minus IR is equal to 0. All right. This is not important. We will need that formula. So QT is equal to CV1 minus exponent minus time RC. All right, one thing that could save some time, well, not much, but it will help us with the calculation is, let's calculate what RC is equal to. So that's the tau, basically the time constant. And we get 10 mega ohm multiply 10 power minus 6. So we get the time constant of 10. All right, so the RC is equal to 10. We're told in part B that time is equal to 5 seconds. So basically, this term is 10, this term is 5, so that will be 5 divided by 10. So let's write this down. We got QT is equal to CV, 1 minus exponent minus 5 divided by 10 over here. So let's compute that value. Okay. So we got 0.393 CV. All right, let's keep it like that. Let's go over here. We got 20 minus 0.393 CV divided by C minus IR equal 0 in this case. All right, so we would like to find that term. This term is the voltage drop, basically. And we are told, when you look at this, and we need... Okay, I'm gonna erase. If you need to pause the video, do it now. I'm gonna erase the top part over here. Again, I'm gonna keep the loop rule here. Okay, so I'm gonna restart over here. This term over here has to be the voltage drop across the capacitor. It is minus 7.86. Note, the capacitance cancel out, so it's 0.393 multiplied by V. V is 20 still. This does not change. And we got IR, it has to equal to 0. This is the voltage drop across the capacitor, across the resistor. So VC is this value, VR is this value. Note, we don't even need to calculate the current in this case because we got already that term. We can isolate that combination over here. So we got VC is equal to 7.86 and VR is equal to 12.14 volt. All right, so these are our answer in this case. So really, when we want to find the voltage on a capacitor or resistor at a given time, we need to find the charge on the capacitor. Once we have the charge on the capacitor, we can find the voltage on the capacitor, and in a series circuit, well, the remaining voltage has to go on the resistance, okay, according to the loop rule. So again, it's not too complicated, but make sure you do practice some of these exercises. There will definitely be something similar in the test. There's no avoiding this section. All right, so in the next video, we are going to tackle Chapter 8, Magnetic Force. So see you in the next video.